Okay, today we're going to cover what I refer to as the Chatlier's principle, still dealing with equilibrium. So let's go through this. Okay, what the Chatlier's principle states is that we can predict how certain changes will affect the position of equilibrium. Now remember, all we talk about with position is that if it's really having to do with what side of the arrow. If it lies to the right, it's going to favor the products. If it goes to the left, then it's going to favor the reactants. And the reality of it is that if we change enough things, we can force it to go in whichever direction that we want. So, okay, if changing concentration, the system will shift away from the added component or towards a removed component. Remember, this is only going to be affected by gases and solutions only, because solids and liquids do not affect the equilibrium expression of certain substances. So again, if we look at liquids and solids, won't affect it. The Haber process, if more nitrogen is added, the equilibrium position shifts to the right, or it means that it starts to favor the products, shifts away from it. And same thing, if we remove some NH3, it's also going to shift to the right, because if we remove this, it's going to shift to change that equilibrium and make sure that it works out correctly. Now, if we change pressure, if we add or remove gaseous reactants or products, it's the same as changing the concentration. So if we change the pressure, we talked about, adding or removing gaseous reactant or product is the same as changing the concentration. So if we change the amount of gas, it's going to be the same as the last one. Now, if we add an inert or uninvolved gas, it's going to increase the total pressure, and it will not affect the equilibrium position. Okay, so an inert gas is not going to have an effect. Okay, not sure why it won't let me highlight. We'll see what happens there. Okay, so next one we have is changing the volume. If we decrease the volume, it's going to decrease the number in gas molecules, and what will happen is that it will shift towards the side with less gas molecules. So this is all going back to that delta N that you had with the Kp and the Kc expression. We got to figure out which side it's going to shift towards. I think you have to write that down. I don't think that part right there is on your notes. So less gas molecules. And then if we increase the volume, it's going to increase the number of gas molecules. It will shift towards the side of the reaction with more gas molecules. In essence, because there's more room to spread out. If we increase the volume, then we've got more space. We're going to have increased gas molecules. If we decrease the volume, we want fewer gas molecules. So that's kind of how that one's going to work. Now, with change in temperature, all other changes alter the concentration at equilibrium position, but they don't actually change the value of K. If we go ahead and we change the temperature, then we change K. So that's just something to kind of keep in mind, that we will change the temperature. And this is just showing you, this is the same thing, ammonia synthesis, so that nitrogen and hydrogen to give us ammonia, and how at different temperatures the K value will change. Okay, so we had lower temperatures, we have that higher K value, and then it will go down. And if energy is added, the reaction will shift in the direction which consumes the energy. The way that I make this one easier is I treat energy as a reactant for endothermic reactions, which makes sense because if I have an endothermic reaction, I'm going to need energy in order for the reaction to take place. You need to write this part down too. This is also not in your notes. On the flip side, I treat it as a product for exothermic reactions. So if it's exothermic, remember I'm going to have a positive delta H, so I'm going to have energy as a product over here. Okay, so now let's just look at some samples. You have the changes, you don't have the answers. So if we add carbon, now remember, if we just look at this one thing to point out, solid, solid, not going to affect it, not going to affect it, gas, gas, will affect it. Remember, the Kp or the Kc would only have these two in it. We would not include the solids. It's going to shift to the left because if I add carbon monoxide, it's going to shift away from that change. Okay? If I add carbon, no change because it's a solid. If I remove carbon, no change because it's a solid. If I add some of this solid, no change. See the repetition here, hopefully we're getting it. If we remove it, still a solid, still no change. If we remove some of our arsenic, okay, then we also, this is a gas, so if we remove the arsenic, it's going to shift to replace it, so it's going to cause it to shift to the right. And if we decrease the overall volume, it's going to shift to the left, because remember, if we decrease the volume, we go to the side with fewer gas molecules. Well, there's no gas molecules over here. They're going to take up less space, so we're going to force it to go left. If we add neon gas, neon is inert. It's not going to have any shift. Okay, no shift. All right, if you look at the next one, I'm going to give the answers here, but what you may want to do is go ahead and pause it here for just a second. See if you can answer the 6 conditions, and then I'll go through the solutions for you. Okay, so if we shift it to the right, hold on. First of all, let's look at solid, no effect. Gas, have effect. Solid, no effect. So if we decrease the volume, again, we're looking for which has the lower gas molecules, so that's why we're going to the right, because there's no gases on that side. If we increase the volume, we're going to go to the opposite, because we're going to the side with the gas molecules. Whoa, runaway answers here. Okay, if we add phosphorus, no change, it's a solid. If we remove chlorine gas, it's going to want to replace the chlorine gas, and since chlorine is a reactant, run out of space, it's going to shift to the left. If we add krypton gas, again inert, no shift. Last but not least, if we add the liquid product, phosphorus trichloride, we're not going to have any of that either. Okay, let's look at a little bit of the energy changes. First of all, you'll notice I put energy right here. So if this is energy, this is going to be a situation where energy is required. So it's going to be endothermic. Okay, so any endothermic reaction, literally just write in energy as a reactant, and then you're going to be able to solve for it. It's actually, I think, pretty straightforward when you do it that way. Now, if we increase the temperature, it's going to go to the right. Okay, it's going to force it to go. It's just like if I increase the temperature, it's just like increasing the concentration of the energy. Since energy is a reactant, it's going to force it to go away from that change or go to the right. If I increase the volume, remember with volume, we're looking at gas particles or moles of gas. We've got 2 on the left as our reactants. We've got 1 on the right as our products. So if we increase the volume, oh, I'm lying. There's 2 here. This is why there's no change. There's a 2 out front. So you have moles of gas are equal to each other, so there'd be no shift. This would also be a situation, since the change is equal to each other, that Kp would be equal to Kc, if you remember that equation as well. If we decrease the temperature, so it's like decreasing the energy, so which means we're going to shift to the left. All right. So just as a summary, in case you need to jot those down. And here's just showing you different temperatures, different pressures, you know, percent by mass. This is just showing you how some of those things change. Okay, and then this is just showing you another system where if you change that, shifts your equilibrium position. It's just summarizing. So I hope that helps. We'll talk about equilibrium next.